Welcome back, students, to our Chemistry 1510 video notes. In this section, we're going to start talking about SI units, significant figures, scientific notation, a little bit of all kinds of review materials. So let's first start with scientific notation. For scientific notation, this is our way to figure out how to quickly write and communicate without errors, very small and very big numbers. And so let's just go ahead and practice what we're expecting scientific notation to look like. And I want to start with this first one right here. And let's ignore the number of significant figure columns right now. Figs, that's supposed to be sig figs, but you knew what I meant. So, and write this in scientific notation. So we're going to pretend that there's like an invisible decimal place, right? So there's an invisible decimal written right there. And what we're going to do is we're going to move that decimal place over 1. And when we move that decimal place over 1, what that is essentially doing is it's telling us that we have an additional place past the ones place here, right? So what we're going to do is write this as 2 times 10 to the first power, because 10 to the first is just 10, and you multiply that by 2 and you get 20. And so this is how we're going to take what's called an ordinary number and write it in scientific notation. So let's do maybe another one that's greater than 1, and then let's do one that's less than 1. So I'm going to come back to these two in a moment. Let's come all the way down to here and write this one in scientific notation. So we're going to take our imaginary decimal place, put it right there. We're going to go over 1, 2, 3, 4, 5. So the number of locations that I moved over was 5. Goodness. That means that up here in my exponent, I'm going to have a 5. Right? So the exponent shows how many places I moved over. And if I have a number that's an ordinary number that's greater than 1, then you're going to expect your exponent to be positive. But if you have something that's less than 1, then your exponent is negative. So let's do one where our exponent is going to be less than 1. So let's come over to the one right above here. So now I have a decimal place written in the value. I'm going to go over now to the other side, right? Because this is something, I'm not moving my decimal place to the left, I'm moving my decimal place to the right because my number is less than 1. So I moved my decimal place over 3 spots. So I'm going to write all of these digits here. I'm going to write all of those down. So I've got 3.050 times 10 to the, well, I moved over 3 places, and because I moved to the right, due to the fact that this number is less than 1, that means I have a negative exponent. So I'm going to have this value times 10 to the negative 3. And if we pause for a moment and recognize that every time I'm utilizing scientific notation, no matter what my ordinary number is that I'm starting with, I always have 1 digit to the left of the decimal. That's key, okay? So you move the decimal place until the decimal point is after the first non-zero digit. So 1 non-zero digit to the left of the decimal. So what I want you to do is I want you to pause for a moment and then practice writing the remainder in scientific notation and then come back and compare your answers with me. All right, so go ahead, hit that pause button, and then let's compare. All right, so let's compare some answers now. So I want you to, again, maybe pause, compare what you wrote with what I wrote. I bet you that I wrote a bunch more zeros than you did, and let's talk about why. So you've watched Tyler DeWitt's videos on significant figures, right? He is such an extraordinary explainer. So now that you've started to be introduced to significant figures, you should be able to look at this column here and write out how many significant figures each of these values has. And this one I actually have to count 6. So the number of significant figures that you have when you are writing an ordinary number needs to translate over into scientific notation. What I mean by that is if I have 3 significant figures written in my ordinary number, I better darn well keep 3 significant figures when I write it in scientific notation. So it's very possible that you dropped those zeros because you didn't think they were important. Well, that's normal, right? You're not a chemist yet. And so chemists certainly think they're important because those zeros were significant from the precision of your measuring device, right? Without those zeros, you used a crappy measuring device. And so these communicate something to us. They communicate the precision of the measuring device that we utilized to take that measurement. So we are going to include all the significant figures necessary to make sure that the sig figs for the ordinary number and the sig figs for our scientific notation value are going to be equivalent to one another. So why don't you go ahead, take a moment, make sure you really compare answers with me, and make sure that wherever I have zeros, you have zeros as well. So as we move on, I've got one more question for you. How about something like 5,700? How are you going to write that to 3 significant figures? So the common wrong things are for people to say, well, what if I put a decimal place at the end? Well, that made 4 significant figures. Okay, so that was no good. And then people will say, well, what if I just do that and then write a decimal place? Now I have 3 sig figs. Oh, but goodness, you dropped a placeholder. And so if you dropped a placeholder, yeah, you have 3 sig figs, but your $5,700 just turned into $570, and that's a problem. You need that placeholder, so neither of those are good. And then sometimes people will say, well, I don't know what to do, so I'm just going to keep it like this. Well, but that's only 2 significant figures. So how do we write this in 3 significant figures? Well, scientific notation is the answer. What we're going to do is write 5.70 times 10 to the third. If we do that, we've correctly put in the exponent, right, of times 10 to the third. And now we have 1, 2, and 3 significant figures. Perfect. So while we're here, let's move into some metric prefixes as well. When we talk about units, metric prefixes often use something that they call base units, right? And your base units are going to be things like a meter, a gram, a liter, and a second. Metric prefixes essentially help us do what scientific notation does. They help us make either very large numbers or very small numbers more manageable. So let's look at what those metric prefixes are. So here's a table of the metric prefixes. Depending upon how your brain works depends on if you like this table or not. If this table doesn't make sense to you, go into Google and type in metric prefix table and find one that works for your brain. Now, the ones that you want to have off the top of your head are going to be listed here. Now let's pretend that you are in a low memorizing mood. Then the ones that are the most important that I expect you to be able to do without really thinking are going to be kilo, centi, and milli. Nano is going to be a close runner-up. The rest of them you really could maybe get away without. Maybe you're going to use the micro at some point, but still, these ones are the ones that you're going to use most often. So knowing how to convert between these units and a base unit is going to be incredibly important. Now, like I said earlier, your brain might not like this table, and my brain also doesn't always care for this table. So let me write down a couple of things in the top here that might help you. So what I have memorized is I have that, and it doesn't matter what your base unit is, whether it's meters or grams or whoever cares, right? Liters. So let's just, I guess, stick with meters. So if we look at 1 kilometer, that's equivalent to 1,000 meters. If we look at centimeters, there's 100 centimeters in 1 meter. There's 1,000 millimeters in 1 meter. And there are 10 to the 9th, which you could write out all of those, but do you really want to? That's supposed to be nanometers in 1 meter. And I'm just going to make sure this 9 is really clearly an exponent so that somebody doesn't think it's 109, right? It's 10 to the 9th power. I just didn't want to write out all the zeros. So what I have is I have these memorized. And there's other ways to write them, right? This is what you see down here, is that a lot of times people switch the way that they write them. They switch it so that they have a decimal place. But what I've found over time is that most students appreciate not using decimals if they don't have to, for the same reason you don't want to use fractions, right? You're just worried you're going to mess it up. And so this, I think, is easiest to memorize. So let's do a practice problem where we're going to use a multiplier here. So here's an example. We want to convert, not converse, 499 centimeters to meters. So the first thing that we need to do is know that there's 100 centimeters in a meter, right? This is our metric equivalency. So we're saying 100 centimeters is the same thing as 1 meter. And so what can we do with that? Well, we can write it two ways. We can write it as a conversion factor, where we have 100 centimeters on the top and 1 meter on the bottom. Or what we can do is have 1 meter on the top and 100 centimeters on the bottom. And then we can use this conversion factor to help us figure out if we should be multiplying or dividing by 100. So we start with what we're given, the 499 centimeters, and we say, okay, we want to get to meters. That's our goal. We need our centimeters to cancel. So if we need our centimeters to cancel, centimeters has to end up on the bottom of the next term. And so if we know that centimeters has to end up on the bottom of the next term, then we use this conversion factor, this one that puts the 100 centimeters on the bottom and the 1 meter on the top. So now our centimeters have canceled out because this is essentially like you saying 499 centimeters times 1 meter divided by 100 centimeters. Well, your centimeters cancel, right? Centimeters divided by centimeters, that's 1. So now you're left in units of meters. Why is this helpful? Because it helps you recognize that you have to take your 499 and divide it by 100. Otherwise, sometimes people accidentally multiply. So your 499 centimeters is 4.99 meters. This process that we just used is called dimensional analysis, sometimes also called factor label method, or dimensional analysis. We're going to talk about dimensional analysis in the last video of this chapter. So I have an area here for you to practice your metric to metric conversion. As always, thank you for your attention. This is Katoni signing out.